So in the last slide, in the previous part of the presentation, we saw that with vertical borehole heat exchangers, we get a radial heat flow with a temperature gradient in the ground becoming smaller and smaller as we move further away. But also we have the effect of superposition, where we have to add up different temperature effects in the ground. This makes calculating the actual temperatures effects relatively complicated, because we are dealing with a small spatial scale, centimeters to meters, and a very large spatial scale, tens to hundreds of meters. And moreover, we're dealing with a very large time scale from weeks and months to decades. So the question is how we can accommodate these calculations in a design approach. This was all developed in the 80s, especially in Sweden. This is from a PhD thesis from Eskilsson, 1987. And this calculation method is implemented in most design codes. The basic method is the finite line source. On the left, we can see a line drawn in the ground volume, where on the line we have all kinds of points. We have point sources, and there is a well-known equation to do the heat transfer around the point source. Integrating all the points on the line, adding them all up, will give us then the solution for a line source, the finite line source equation. If we want to have a boundary condition at the surface of no temperature change, we use a little trick where we have a mirror source above the surface with a inverted heat flow. So near to the surface, where the points of the mirror source and the actual source are relatively close, the heat flow cancels out and the temperature effect is small. And going deeper, the distance between a point on the line and on the mirror source becomes bigger, so the cancelling effect becomes smaller, and at a certain moment there is no cancelling effect anymore. So in this way we can calculate the temperature effect in and around a borehole, but also the temperature effects between boreholes. Now, of course, this depends on how the boreholes are positioned in space. We can have all kinds of different configurations, and because we have many time steps and a long time period, the computation is still very costly. So another trick then is to use so-called G functions. These G functions, what you do is you calculate the temperature change in the borehole heat exchanger system for one particular time step with one particular change of heat rate, and then we use this to calculate a characteristic function, the G function, that tells us how the whole array will respond to changes in heat load. An example is the graph that we see in the middle, where you can see the dimensionless G function as a function of log of the time. And this is valid on the top left, you can see, for a 3x2 heat exchanger configuration. What we also need to do is decompose load steps, but that is more a technicality in the computation, so we won't go into that. Another process that we have to deal with is the actual heat flow between the fluid in the heat exchanger and the surrounding ground. The temperature difference between the fluid and the borehole wall governs the heat extracted. So the temperature that we need to extract the delta T, to extract a certain amount of energy, Q in watts per meter, is affected by the thermal resistance of this borehole heat exchanger. And this thermal resistance of the borehole heat exchanger is made up of different components. For instance, we have a thermal resistance from the fluid to the pipe wall. There is a thermal resistance across the pipe wall. As you can see, the downflowing channel and upflowing channel are positioned, let's say, not too far from each other. Typical for a U-loop heat exchanger would be something like 5 or 7 centimeters, maybe 10 centimeters. In a concentric heat exchanger, the one flow channel is actually inside the other flow channel. So there is heat exchange between the two flow channels. The pipe-to-pipe thermal resistance tells us how big this heat exchange, this heat loss is. And of course, we also have the borehole filling material and the borehole radius itself. Here we can see it in a little schematic where we see all the different thermal resistances between the different components in a U-loop ground heat exchanger. Between the warm and cold pipe, R12, the fluid resistance, TF1, the resistance between pipe 1 and the borehole wall, and between pipe 2 and the borehole wall. All these resistances have their own equations, let's say, can be calculated and added together.